Good morning. Today I'll be explaining how to find the Cartesian equation of a circle and also determine the minimum and maximum modulus for the complex number problem where our center of circle is 3 plus 4 imaginary units and our radius is equals to 2. First, we use the standard equation for a circle in complex number where our modulus z minus center of circle equals to r. Since z equals to x plus y imaginary units, we can substitute this into the equation. So x plus y imaginary unit minus 3 plus 4r imaginary unit will equals to 2. We will get our x minus 3 square plus y minus 4 square equals to 4. This is the Cartesian form of equation of the circle with radius of 2 at coordinates 3. Now I will explain the general proof for the formulas of the minimum and maximum points on the circle. We start with our equation. Our z, modulus z minus center of circle plus modulus equals to r. This represents a circle with center zo and our radius r. We let z equals to x plus y imaginary units and our zo will be xo plus yo imaginary units. Substituting into the equation gives the Cartesian form of the circle x minus xo square plus y minus yo square equals to r square. We're going to be talking about the argument extrema. Today I'm finding the smallest and the largest angles formed between a tangent line to a circle and the x-axis. These are called the argument extrema. First, I define the angle in terms of gradient m of the tangent line. Since the angle a line makes with the x-axis depends on its slope, I just need to find the minimum and maximum values of m.
What's up, guys? Welcome back to Advanced Maths Season 3 Part 8. Today we're dealing with equation of locuses and we have an ellipse right here. The two foci are given at the beginning. But before we do anything, we first have to convert everything to Cartesian form. So here we just expand everything, and then it's important to take note that we get the final result in the form of x minus h over a squared, the whole thing, plus y minus k over b squared, the whole thing, equals some constant. Only then do we reach the Cartesian form, and can we do something else.
Alright, it's your boy, the optimization specialist. As a specialist, my job is to differentiate equation that comes into me. Now we have to ellipse and circle. We differentiate both of them so we can equate them later. We equate them later to find what x equals to and what y equals to. That's my work over there. See, y equals to something. And now when I got y equals to something, I substituted it back into the original formula. And we got this long algebra equation of what x equals to. And from there, we got 4 values of x. But 2 of those solutions exist in the imaginary plane. So we only accept 2. We have one, x equals to 12 something, and the other, x equals to 7. From there, we can see one is z max and the other is the z min. That's all.
Now on to the argument. We're finding maximum and minimum argument. So the way we calculate it is just using y equals mx. So this straight line from origin, when it intersects with our ellipse intersection, because it's the maximum and minimum, there are only one point that's in contact. So we can use discriminant equals 0 right here, or basically b squared minus 4ac equals 0. And using this, we will get 2 results because they're square. There are 2 roots or 2 values, one for minimum and one for maximum. And now that we have both these, we can just sub in to the original formula and find, using negative b over 2a to find x, and then using x to find y. Then we find the complex values that suits this equation of minimum and maximum argument of this ellipse.
So this is basically the graph for the GeoGebra illustration for a circle. On the bottom here, I will show the formulas that we use to graph this circle. So the first one, the main part, is the purple circle here, as you can see, and this is the formula we use to make this circle. As you can see, there's 2 lines which are red and blue there, and these 2 are the tangent rays that are the minimum and maximum gradient that touches the main circle. And then there's also a sweeping circle here, that is to determine the z min and the z max from the origin. And here's a clip of me sliding the sweeping circle so that it moves to the z min and the z max. So for the graph of ellipse is basically somewhat same as the graph for circle. Here is the graph, and I'll show the formula also. For the main part, the ellipse, this is the formula we used. And for the red and blue tangent rays, these are the 2 formulas. And last but not least is the sweeping circle. We also use this to determine the z min and z max of the ellipse from the origin. And this is a clip of me sliding the sweeping circle so that it touches the z min and z max.